This is lesson 15 of industrial instrumentation. We will continue with the flow meter. So, this is the lesson 15 and we will basically discuss the Flowmeter 4. We have given the name like that. So, in this lesson we will cover the contents of the lesson: electromagnetic flow meter, ultrasonic flow meter. These two basic flow meters we will discuss in this particular lesson. Now, let us look at what the viewer will know at the end of this lesson. At the end of the lesson, the viewer will know principle of operation of electromagnetic flow meter, type of pipe used, because various types of pipe you have to use, the magnetic field excitation for the flow meters, because electromagnetic flow meters it needs some magnetic field excitation. Then we have its advantages and disadvantages. Principle of operation of ultrasonic flow meter. This also we discuss the ultrasonic flow meters in details. So, it will come one by one. Now, let us first start with the electromagnetic flow meter. Electromagnetic flow meter is limited to the measuring the volume flow rate of electrically conductive fluid. The conductivity of the fluid should be greater than 10 micromole per centimeter. These are typical restrictions of the electromagnetic flow meters, and if it is less than this, so this flow meter will not work. However, there is no higher limit on the greater conductivity of the flow meter. Right, you will see that in some situations that the pipe as well as the electrode installation will be different if the conducting liquid is a very good conductivity of the fluid which is flowing to the pipe. The schematic of electromagnetic flow meter is shown in figure 1. Let us look at. The instrument consists of a cylindrical tube made of stainless steel fitted with an insulating liner. So, there should be insulating liner, because if it is a metal tube, so it will have a short circuit path. So, for that reasons what we will have, that we should have an insulating liner. Now, typical, you see this is the electromagnetic flow meter. It looks like this. You see, if I have a camera on this side, camera on this, it looks like this, right. So, the liquid is flowing in through it and it is coming out, okay, flowing in, coming out. So, there is a magnetic field. So, there is a coil on top and the coil at the bottom. So, it will produce magnetic field which acts perpendicular to the flow of direction of the flow of the fluid, and we will put two sensors on the both side, one sensor here or electrode, another electrode here. So, you will see that due to Faraday's law of electromagnetic inductions, some voltage will be developed across this electrode. That voltage will be calibrated in terms of flow. Now, the flow of the fluid, this position of the electrodes, the line connecting the two electrodes, and the direction of the magnetic fields are mutually perpendicular to each other, right. You see here fluid flowing through the pipe, there is insulating liner. So, we are producing magnetic field, okay, with proper coil and all those things, and two sensors are there which are installed diametrically opposite side. One sensor is here, another sensor on the other sides, I am sorry. One sensor is in this side, other sensor on the other side, you cannot see that, and we are getting in the output voltage. This output voltage is to be calibrated in terms of the flow. The typical lining materials are neoprene, polyterafluoroethylene, which is abbreviated as PTFE, and polyuroethane. The magnetic field that is perpendicular to the direction of flow of the liquid is created in the tube by installing energized field coils in diametrically opposite side of the pipe. This already we said, I mean, two energized field coils are there. What type of what type of energy will apply, that we will discuss later on. But to produce magnetic field, we must have some two coils which are diametrically opposite side. The voltage induced in the fluid is measured by two electrodes inserted into the opposite sides of the tube. Okay, we have shown just right now, right? Two electrodes are there. These also installed in the diametrically opposite side, but all are mutually perpendicular to each other. The ends of the electrode are flush with the inner surface of the fluid carrying pipe. This is important for the magnetic flow meter, especially if the conductivity of the fluid is not very high. If it is very highly conductive, then it is not necessary to put it to be flushed with the pipe, right. The material used for making the electrodes are stainless steel, platinum, iridium alloys, titanium and tantalum. You can see that electromagnetic flow meter, though it has many advantages that we will discuss what are the advantages later on, but it is not very cheap instrument. It is a quite expensive instrument in the sense that the type of electrodes you will use, the pipe you use, and the pipe is not expensive, but inside the pipe you should have a liner, so those are quite expensive. That makes the instrument very expensive. Moreover, individual calibration of the instrument is necessary, very precise calibration. To make this, if you add all these things, you will find that the initial installation of this tube is quite expensive compared to the other flow meters like differential pressure flow meters and all those things. But in some situations we cannot afford to have a differential permanent pressure drop. In that type of situation, this magnetic flow meter is used. The material used for making the electrodes are stainless steel, platinum, iridium alloys, titanium and tantalum. In accordance with the Faraday's law of electromagnetic induction, voltage E induced across the length L of the flowing fluid at a velocity V in a magnetic field of flux density B is given by E equal to VLV volts. Okay, right. So let us look at what is this. Okay, this is our pipe. So you see what is capital L. Capital L, basically if you look at here, capital L will be the, if I take some pen, so capital L will be the diameter of the pipe, is not it, inner diameter of the pipe, capital L. V is the flowing velocity of the flowing fluid and V is the magnetic field, which is magnetic field intensity or flux density, which is working on the conductive fluid, right. So we can see that in accordance with the Faraday's law of electromagnetic induction, the voltage E induced across the length L of the flowing fluid flowing at a velocity V in a magnetic field of flux density B is given by VLB. So where you can find this in volts, obviously. Okay, you can see this is in volts, right, this output voltage in volts, provided that where B is the flux density is in Weber per meter square, which is in Tesla, L is the distance between the electrodes or inner diameter of the pipe, which is in meter, V the velocity of the fluid, that is in meter per second, right. See, if you use all these notations, you will find that the velocity of the, the output voltage of the fluid will be in volts. And you can see here, if BA and L remain constant for a particular liquid, obviously E will be directly proportional to the flow velocity. So if you now multiply that velocity with the area of cross section or the inner area of cross section of the pipe, we will get the volumetric flow rate, is not it. Now advantage, there are several advantages of this type of flow meters. Number one, there is no obstruction of the fluid flow, therefore there is no pressure loss associated with the measurement, right, this is very important. Then we have, it is suitable for installation that can tolerate only a small pressure drop. In many situations you see this pressure drop cannot be allowed when the liquid is flowing a slow moving velocity and pressure across is very small. You will find that we cannot afford to have this type of pressure drop, right. So in that of situations this magnetic flow meter is quite popular. The absence of any internal part is very attractive for measurements of velocity of corrosive and dirty fluids. You will find that in other type of flow meters, whether it is differential pressure flow meter, turbine flow meters, everywhere we have to install all the systems inside. In the case of turbine flow meter, entire turbine is to install inside the pipe. Though in the case of orifice meter or venturi meter, there is no such installation, but there is orifice plate is there and also in the case of venturimeter there is a slight reductions of the pipe diameters, which is actually the throat of the pipe. Okay, that also makes problem. So the absence of any internal part is very attractive for measurements of velocity of the corrosive and dirty fluids. So the operating principle is independent of fluid density and viscosity. These are very important, and the output voltage is proportional to the average velocity of the fluid. This is average velocity of this is very important point. Please note, the voltage is proportional to the average velocity of the fluid. The operating principle is independent of the fluid density and the viscosity, right? That what does it mean? That is it independent for all the liquids? The output voltage will remain same if the velocity is same? It's not true. Why will be explained after some time. Got it? What I am saying? That means I am saying that our equations, if you remember, is E equal to VLV. So we are saying that a B is proportional to V. So for all liquids, if the velocity is same, will I get the same value of the output voltage? Not true, you won't get. The reason is L will remain fixed. That is the inner diameter of the pipe, because we will install, this is basically distance between the pipe. It assumes like this one, we can assume this like this one. If I again take this example, that a conductor is moving inside, a conductor of length is moving inside a magnetic field. If I assume it is of length of L, so that conductor of length L is moving inside this pipe with a velocity V, that we can assume. Okay, we apply the Faraday's law of electromagnetic induction also by using that principles. A conductor of length L, which is inner diameter of the pipe, moving with a velocity V under the flux density B. Clear? So there is no difficulty of measurement of the either laminar and turbulent flow. This is very important since it is independent of viscosity and density. So obviously we can measure both laminar and turbulent flow. It has accuracy of plus minus 1% of indicated flow. This is also quite high, I should say. The flux density, now what I said some time back, that whether for the same velocity I will get for the different liquids, will I get the same value of the voltage? No, that is not correct. Why? It will be clear now. You see, the flux density B is related to the fluid intensity H by the relation B equal to mu H, right, where mu is called the absolute permeability and is expressed in Henry per meter, and the absolute permeability of the another material can be expressed relative to the permeability of the free space equal to mu r into mu naught, where mu naught is the permeability of the free space. Its value is 4 pi into 10 to the minus 7 Henry per meter, and it is a constant. That mu r is a dimensionless quantity and is called the relative permeability, and its value depends on the material of the fluid, right. So as the material of the fluid changes, value of the mu r will change, so value of mu will change. So that will lead to the value of B will change, so the output voltage also will change, right. So for different liquids I will get different outputs depending on how much the value of the mu for that particular liquid. Like other forms of flow meter, the electromagnetic flow meter requires a minimum length of straight pipe work upstream from the meter in order to guarantee the accuracy of the measurement. We have seen that this type of restrictions we have, especially in the differential pressure flow meter. That means 20 upstream pipe diameter, there should be no obstruction, no pipe bendings, that type of things also here. Saying that like other forms of flow meter, the electromagnetic flow meter requires a minimum length of straight pipe work upstream from the meter in order to guarantee the accuracy of the measurement. No pipe bending or pipe fittings are usually allowed in 5 pipe diameter upstream. So it is quite less compared to some other flow meters. We have seen that times in many flow meters it is 20 pipe diameter the upstream. Please note that one thing is very important, it is measuring the average flow velocity, right. Now disadvantages, one of the greatest disadvantages, the conductivity should have some minimum value. If it goes below that, magnetic flow meter cannot work. So this excludes by this all the hydrocarbons. That means electromagnetic flow meter is not suitable for measurements of the fluid in any petroleum industry. Okay. So there are some restrictions here and restrictions of the petroleum industry of using any electrical type of system because of hazards. I mean, it's inflammable. But still, if you don't consider that part, you will find that electromagnetic flow meter will not work for the hydrocarbons because hydrocarbons conductivity is much less prescribed for the electromagnetic flow meter. So that I will discuss one by one. The electromagnetic flow meter requires a minimum conductivity of 10 micromole per centimeter. Right? Therefore, it is not suitable for measurements of flow of gases and liquids of liquid hydrocarbon. So, it is not suitable for measurements of liquid in any oil industry or petrochemical industry. Right? It is suitable for measurement of flow of slurries provided the liquid phase has adequate conductivity. Okay? Adequate liquid phase must have adequate conductivity, then only the measurement is possible. Otherwise, it cannot be. So, that restriction is there, micromole per centimeter, it should be there, right. Now, instrument is expensive as I told you earlier in terms of initial purchase cost, because I told that the cost of the inner liner of the pipe, cost of the electrode, these are also expensive, and cost of calibration is also quite high. So, one of the reasons for high cost of the need is the need for the careful calibrations of any instrument individually during manufacture, as there is considerable variations in the properties of magnetic material is used. You see, that is very difficult to get actually predict the B, I mean the amount of value of B you will get. So, it will slightly vary depending on, even though you are giving some coil, okay, a slight reorientation, so the slight misalignment of the coil will give a different value of B. So, your output voltage. So, each and every meter should be calibrated on the site. Okay, and separately is to be calibrated. That is not one meter you have calibrated, you can say the other meters have same calibration value. That is not correct, right. So, these are the difficulties along with the initial purchased cost. That means your pipe is quite expensive as well as the electrodes are also expensive. So, keeping these three minds, I mean keeping these 3 points, electromagnetic flow meter is more expensive than the other conventional flow meter. But there are some advantages, as I told you. One is the greatest advantage, that it does not create any pressure loss, right. That is the greatest advantage of this electromagnetic flow meter. Now, field excitations, what type of field I will give, because I have to give some field excitation for the this electromagnetic flow meter to work, right. There are 3 possible ways of energizing the magnetic field coils, and they are DC, by you can direct current you can give to the field coil, it will produce some DC voltage. It does not matter, the pipe is, I have a DC magnetic field and the fluid is moving inside the pipe. So, there is no harm. Okay, I will get a Faraday's laws of introduction. So, there is a rate of change of flux. Okay. So, that will be converted into the voltage. We can as well have AC with 50 Hz AC we can have also. That is another way of energizing the magnetic coil. 2 magnetic coils, so one at the top and other at the bottom, right. So, what type of electric energy we will give, either DC or 50 Hz AC or pulsating DC or interrupted DC. This is another method. We will discuss this pulsating DC in details, right, because that is the most modern method of energizing the field coils for an electromagnetic flow meter. The 3 common difficulties faced by the DC excitations are polarization. If any DC has a polarization effect, okay, we know, because any DC has a polarization effect. This is a very typical problem whenever you use any DC. There is the electrochemical effect, because there is if there is a liquids, there is a chance of electrolysis. So, the positive ion will move in one side, negative ion will move in another side. So, all these problems will be there, and also thermoelectric effect, because there is a dissimilar metals. So, whenever you apply DC, if there is difference of temperature, so I will get a different, we will get additional voltage for which we have not accounted for, right. So, that will give some error in the measurement. So, all this will influence the DC output voltage. Okay. So, what is the solution? Solution is these effects can be overcome by energizing the field coils with alternating current of 50 Hz. We can apply 50 Hz signals, alternating signals, right. So, and it is used for over the years, right. For many years AC excitation was most common, and signals can be easily amplified by high gain AC. This is another advantage of the AC, because DC amplifier was not popularly available some time back also. So, now DC amplifiers are available, but as you know, op-amp has some restrictions of the currents and how much maximum voltage you will get, that things are there. but if you have AC amplifier, it is easy to amplify the signal. Now, the major disadvantage of AC energized field coil is the output voltage is subject to 50 Hz interference voltage generated by the transformer action in a loop consisting of the signal leads and the fluid path, right. Signal leads are there, okay. We have a fluid path is there, so in between there is a transformer action. That will create problem in the case of AC magnetic field when you are using AC 50 Hz. The problem of DC and AC magnetic fields can be solved by energizing the coils with pulsating DC or interrupted DC. We will use some interrupted DC, right. So, that to solve this type of problem, neither there will be any DC problem like polarization effect, then electrochemical effect, then thermoelectric effect, not those transformer feedback actions which is common in the case of 50 Hz AC energized magnetic field. So, this we can discuss in details. It is a direct current that is pulsed at a fixed interval, right. The pulsed magnetic field and the induced or output voltage of the flow meter is shown in the figure 2. This is the figure 2 we can see here. So, magnetic flux produced by the field coils and the output voltage of the flow meter. Okay. There is a non-zero voltage here. So, that is called the zero error in the case of electromagnetic flow meters. We will discuss this. So, the output voltage I can write equal to E2 minus E1 plus E3 by 2 whole minus E4 minus E3 plus E5 by 2, right. Here the DC field is switched in a square wave fashion between the sum value and 0 at a frequency of 3 to 6 Hz, right. When the field is 0, any non-zero output from the flow meter is considered to be an error. It is called the zero error. Okay. When the field is 0, you see here, when the field is 0, so we have some non-zero output voltage. When the field is 0, we have a non-zero output voltage. When the field is 0, we have a non-zero voltage. So, these are the zero error. Clear? When the field is 0, any non-zero output from the flow meter is considered to be an error. It is called zero error, right. By storing this zero error, storing the zero error and subtracting it from the output obtained when the field is next applied, the error can be removed, and the principle is similar to the auto zeroing of digital multimeter. When the input is momentarily grounded and the non-zero output voltage charges a capacitor, this capacitor voltage can be utilized later to correct the output in the case of actual reading, right. In the case of digital multimeter, as you know, also we have A to D converter and other circuitry. So, you will find that even though if I short the output, okay, I will getting some display on the meter, so which is undesirable. So, what they do actually in the case of digital multimeter, same principles we are utilizing here also, they are charging one capacitor by that offset voltage by shorting the input. Okay. So, that voltage will remain intact. So, whenever I will make the actual measurement, so we will add algebraically that voltage to the measured voltage. So, it will be either subtracted or added. So, I will get the actual reading. In practice, the zero error correction is done several times in a second in the case of flow meter, electromagnetic flow meter. Now, there is situations when the electromagnetic flow meter you can have a metal pipe also, you do not need lining, all these things which is expensive. That type of situation will arises when the velocity of the fluid you are measuring, and the fluid has a very high conductivity. One of the good example as suppose you are measuring the fluid velocity of a mercury. And mercury may flow through a stainless steel pipe, that is quite desirable, it should flow through a stainless steel pipe. In that situation, you do not need any liner, any lining, inside lining, because that the conductivity of the mercury is so high, it is even higher than the stainless steel. So, even if you put some sensor outside, probe outside, so it will pick up the signal that shortest path, right. For measurement of flow of liquid that has high conductivity, the metal pipe without insulating liner is used, that I said. For an example, the liquid is mercury and stainless steel pipe will be used. Here the conductivity of the mercury is much higher than that of the stainless steel, right. The electrode in this can be installed on the outside surface of the pipe, that is very important. So, you can install the electrode just outside the pipe, right, because it will not shorten, right. So, that is the we talked about the electromagnetic flow meters, their advantages, Only disadvantage that it cannot measure the flow of the hydrocarbons and all these things. Other things, it is expensive also. Well, how much it is rugged, that depends. Obviously, it will not rugged as our differential pressure flow meters, which is used over the years. Little lit, I mean, it need very little attention also. So next flow meter, also in non-invasive types, we will discuss is the ultrasonic flow meter. Right? Go to the board, digital board. Yes, ultrasonic flow meter. You see, the ultrasonic signal is a short burst of sine waves when the frequency is above the available range of the frequency, which is 20 kilohertz. This is non-audible range, right? So above 20 kilohertz, even here in the stream. So above that frequency, we call it ultrasonic frequency. Now typically the ultrasonic frequency wave is around 10 megahertz, but we will see that we can have frequency anything between 0.5 megahertz to 10 megahertz. The ultrasonic measurement of the volume flow rate is a non-invasive method. This is again a non-invasive method of measurements. There is a great advantage of this type of method. We will see, I mean, later on. There are two types of ultrasonic flow meters. So basically, they are Doppler shift flow meters and there are time shift transit time measurement flow meters. One is Doppler shift flow meter, that is another is transit time measurement type flow meters. We will discuss both the cases. There are some, I mean, situation where you have to use Doppler shift, in some situations you have to use transit time measurement technique. Both the method depends on the transmitting and receiving of acoustic energy. Okay, acoustic energy is to be transmitted and received, and we usually use piezoelectric crystal for that. The piezoelectric crystals are used for both the functions. In a transmitter, electrical energy in the form of short burst of high frequency voltage is applied to the crystal, causing it to vibrate. That vibration now communicates to the through the liquid, and it ends the another diametrically opposite side of the pipe, where there is another sensor which will pick up the signal or receive the signal. Right? The crystal is in contact with the fluid, and the vibration will be communicated to the fluid and propagated through it to what far? To the point where the other sensors are there, diametrically opposite side. The vibration reaches the receiving crystals, which is produces an electric signal as an output, right? Now let us, this is the basic principle so far I discussed about the, in both the cases Doppler shift ultrasonic flow meter and transit time measurement flow meter, this is the basic principle. So we will use some ultrasonic piezoelectric crystals, we will transmit the signals, okay, and we will receive the signals. Now Doppler shift ultrasonic flow meter, it looks like this. Principal operation, let us look. A fundamental requirement of this instrument is the presence of scattering elements within the flowing fluid. Okay, very clean fluid, if the liquid is very clean, if the gas, we cannot make the flow measurements in that type of situation. What I am saying, the Doppler meters will not work unless sufficient reflecting particles and or air bubbles are present in the fluid itself, so in which we are interested to measurement the, because it is to be reflected, right. So we will show that thing in the figure. These flow meters usually employ clamp on configuration as shown in figure 3. You see, this is our configurations. I am transmitting the signal from this, right. You see here, I am transmitting the signal from this is coming down here. This is reflecting particles. So it is getting deflected with an angle theta, and I have a receiver here, right. So there is a change of frequency, we will measure that frequency and calibrate in terms of flow. So fluid is flowing through a velocity v, right, and this is a clamp on measurement. That means you can externally clamp on these meters, even though we are showing there is some deviation, some refraction, so that is I am not showing in details here, right. This Doppler shift ultrasonic flow meters. The transmitter propagates ultrasonic wave of frequency ranging from 0.5 to 10 megahertz in the fluid, which is flowing with a uniform velocity of v. The particles or bubbles moving with the same velocity will reflect some of the energy to the receiver, right. Some of the energy will be received by the receivers, which is again as piezoelectric crystals. The reflecting elements cause a frequency shift between the transmitted and reflected ultrasonic energy. The frequency is measured and it is calibrated in terms of flow velocity. It is calibrated in terms of flow velocity, and the flow velocity v is given by c ft minus fr 2 ft cos theta. What are those legends? Ft is the frequency of the transmitted ultrasonic wave, Fr is the frequency of the received ultrasonic wave or reflected ultrasonic wave, C is the velocity of sound in the fluid being measured, theta is the angle of incidence and the reflected ultrasonic wave that make with an axis of the flow in the pipe. See, now you see here we have to know the C very accurately in the medium itself, okay, because your accuracy of the entire measurement depends on how accurately you know the velocity of the sound wave, ultrasonic wave in that particular liquid, right. That is to be found earlier, then only you can find the velocity. But whereas you will see in some other methods this is not necessary, it will cancel out, right. That is in those methods are preferred. Transmitter and receivers are made of piezoelectric oscillator technology. The Doppler shift flow meter is relatively inexpensive. This is quite inexpensive instrument. The measurement accuracy depends on the flow profile, the constancy of the pipe wall thickness, the number, size of the reflecting particles, and the accuracy with which the velocity of sound in the fluid is known, right. So, these are the all thing which will be necessary for accurate measurements of the fluid velocity in a pipe by ultrasonic method of Doppler shift. The accurate measurement can only be achieved by carefully calibrating the instrument in each particular flow measurement application, right. That is also, so you have to again, like electromagnetic flow meters, you have to calibrate individually in all cases, okay. That restricts the use of these instruments a lot, but it is quite popular for some other applications because it is totally non-invasive techniques. Recently the Doppler shift ultrasonic flow meter has been developed with the transmitter receiver flush in the inner surface of the pipe. In this the problem of variable pipe thickness can be avoided, because in the clamp on method you have to install the ultrasonic flow meters on the outside, right, ultrasonic flow meter outside the pipe. But recently the Doppler shift flow meters has been developed with the transmitter and the receiver flush in the inner surface of the pipe. In that type of situation the variable pipe thickness cannot be avoided, because you see if there is a variation of the pipe thickness, that will cause a problem, because you will launch the ultrasonic waves outside, so it is coming through some wedge, then it is coming to the liquid. But this type of problem can be solved if you install if the sensor, ultrasonic sensor, is flushed with the liquid itself, right. However, we must note following points while measuring the fluid velocity shift flow meter with the clamp on design. Dependence of C, velocity of sound in fluid cause compensating changes in cos theta. For such a design, theta is transducer wedge angle and C be the propagation velocity of the wave in the wedge material. What is that? We can look at, if I look at ultrasonic flow meter, this here you see here, okay, this is the wedge inside which we have put. So, the velocity of the fluid in the inside of the ultrasonic in the wedge is more important at that time. We must know that accurately also, right. So, those are the problem with the ultrasonic flow meter. That is people now, because there is a refractions also of the ultrasonic wave, so if they want to flush it with the liquid itself. Okay. Dependence of C, velocity of sound in the fluid causes the compensating changes in cos theta. For such a design, theta is transducer wedge angle and C is the propagation velocity of the wave in the wedge material. Now, let us start to discuss the transit time ultrasonic flow meter. This flow meter has some tremendous advantage over our conventional Doppler shift flow meter. So, let us discuss that. The transit time ultrasonic flow meter is designed for measuring the volume flow rate in a clean liquid or gases. This again the problem, in one cases you need dirty liquids and another case you need clean liquids or gases. If the liquid is dirty, we cannot make the measurement. It consists of a pair of ultrasonic transducer mounted along an axis aligned at an angle theta with respect to the fluid flow axis, right. It will be more clear once you see the diagram of this. Transit time ultrasonic flow meter is shown in figure 4. Next figure. Each transducer consists of a transmitter receiver pair. So, each transducer is a transmitter receiver pair, and transmitter emits the ultrasonic energy which travels across to the receiver on the other side of the pipe, right. You can see here. So, this is the transmitter, okay, and this is also receiver. So, this comes here, receives, and it again transmits, right. Fluid is flowing through the pipe, there is an angle theta. The fluid flowing through the pipe causes a time difference between the transit times of the beams traveling upstream and the downstream, and measurement of the difference of the time travel gives the flow velocity. What is that? So, when the liquid is coming, when the this ultrasonic wave is traveling in this direction, this is upstream direction because it is moving, and when it is flowing, when the ultrasonic waves is coming back, it is in the opposite side of the direction. So, there is a time shift between the two, right. Received signal transmitting between the time elapsed between the signal transmitted and the received, it will be different in two cases, right. So, using that principles I can measure the you see here, the fluid flowing through the pipe causes time difference between the transit times of the beams and traveling upstream and downstream, and the measurement of the difference of time travel gives the flow velocity. Typically, the time difference is 100 nanoseconds in a total transit time of 100 microseconds. This is again the problem, how do you measure such a small value of time? You have to measure it very accurately, right. So, the accuracy of the measurement of fluid velocity comes down, boils down to the measurement of time difference of 100 nanoseconds. So, how do you measure this time shift? So, methods of measuring the time shift, there is direct measurements, conversion to a phase change, you have a conversion to a frequency change. We will discuss the frequency change in more details. The third method is attractive since it does not need to measure the speed of the sound of the measured fluid, because in previous case in Doppler shift flow meters we have seen that we need the we have to measure the fluid velocity, which is not necessary in this case, right. The method also multiplexes the transmitting and receiving functions, so that some transducer can be used both as a transmitter and receiver. Okay. Some multiplexing signal should be there. When the transmitter is working as a transmitter, during that time you should not receive any signal, right. So, some multiplexing functions arrangement you have to make, which shoots again the cost of the signal processing circuitry of this type of transducers. The forward and reverse transit time across the pipe is TF and TR are given by C plus V cos theta, right. If I take this, okay, I can draw it here nicely, okay. I have a pipe here, I have a signal here, we are receiving signal. So, this is the transit time when it is going back, okay, forward and reverse transit. So, is it how much it will be? This is the L is the length between the two sensors, this is L actually, please note this is L, okay, small letter L, this is small letter L, right. This difference between the position of the two sensors is the velocity of sound plus V cos theta, because this is cos theta you have shown, is not it. So, this is theta, right. So, this is cos theta. So, V cos theta, so that is the time. Similarly, here also it will be C minus V cos theta, right, because in that case what will happen in case of return, because signal is going in these directions, is not it. It will take more time obviously to reach the transmitter here itself. Where C is the velocity of sound in the fluid, V the velocity of the fluid, L is the distance between the ultrasonic transmitter and receiver, okay. Theta is the angle between the ultrasonic beam and the axis of the fluid flow, right. Now, time difference delta t is given by delta t equal to TR minus TF if you subtract 2 VL cos theta upon C square minus V square into cos square theta. Clear? However, the actual practice, the receipt of the pulse is used to trigger the transmission of the next ultrasonic energy pulse. This is necessary, otherwise how will a machine will know. So, the receipt, whenever we will receive the pulse, we will trigger some signal conditioning, so that it will launch the next ultrasonic pulses to the transmitter itself. Even though that time it is a transmitter, and the transmitter where I have received the signal from is actually now receiver. Thus, the frequency of the forward and return pulse trends are given by inverse of ff equal to 1 by Tf c plus v cos theta by L, fr equal to 1 by Tr c minus v cos theta by L, right. See, if I take this frequency shift, thus the frequency, I mean, if the two frequency signals are now multiplied together, the resulting bit frequency is coming, okay, difference and the sum frequency will come out 2v cos theta by L if the difference frequency. So, v is L delta f 2 cos theta. If L and 2 cos theta are same fixed, so delta f we can see is directly proportional to the velocity of the fluid flow, right, which is flowing through the pipe. The two frequencies ff and fr are mixed in such a way that the received signal contains a bit frequency that are their sum and difference frequency. So, that different sum frequency we can easily pass through a low pass filter. So, only the bit frequency will remain, difference frequency will remain, other frequency will go away, right. And FFT analysis of this output will lead us to a peak corresponding to the difference frequency, which is a measure of the flow velocity, right. FFT analysis will do. So, we will get a peak. So, that will give you about the flow velocity. Peak corresponds to the difference frequency. So, we will get a peak corresponds to difference frequency, which is the measure of the flow velocity. Now, transit time measurements is shown in figure 5 that we can see. So, this is our transit time measurements. You have a multiplexer, it will activate whether this will be transmitter or receiver, and this have a receiver signals and will have a circuit. If the pipe diameter is large, then the transit time flow meter is preferred over the Doppler shift flow meter, because we are get that at that time the transit time will be large and it will be easy to measure the large time difference. Okay, the delta f also will be large in that case, because we are not measuring the time, ultimately we are converting to frequency and time, frequency and we are measuring the frequency. So, if the transit time is large, so obviously what will happen, your delta f also will be large. The accuracy is typically 0.5%, that is the typical accuracy of our flow meter. The instrument cost more than a Doppler shift flow meter because of the greater complexity of the signal conditioning circuitry, right. The circuit is more complex than the Doppler shift, but the advantage that we do not have to measure the velocity of sound in particular liquid. So, that is why I am saying the instrument cost more than Doppler shift flow meter because of the greater complexity of the signal condition circuit needed to make accurate transit time measurement, right. Now, advantage of these ultrasonic flow meters, let us look at one by, this is in general, I mean not only the flow meters, Doppler shift flow meters or transit time measurements flow meters, I am talking of the general advantage of the ultrasonic flow meters, right. There are several advantages of the ultrasonic, that is the reason it is slowly coming up. You can say now the market share is around 10%, but market share of the flow meters in the process industry you will find it is 10%, right. The fluid flowing through the pipe is not necessarily to be conducting fluid. This is very important advantage, we should say that, because in case of you will see that the electromagnetic flow meter it must be conductive fluid, that restriction is not there, right. It is particularly useful for measuring the flow of corrosive fluids and slurries, right. So, if you have a corrosive fluids and slurries, even though it is not conductive, because in the case of fluid slurries we have seen that in the case of magnetic flow meters the liquid portions of the slurries should be conductive, otherwise you cannot use the flow measurements of the slurries by the electromagnetic flow meter. But in this case any slurries, okay, if it is conductive, non-conductive, it does not matter, I can make the measurements, right, by the ultrasonic flow meter. A further advantage, again I repeat, these ultrasonic flow meters advantage in general, right. A further advantage of the over other flow meters is that the instrument is one which clamps on externally to existing pipe rather than being inserted as an integral part of the flow line, right. It happens in the case of electromagnetic flow meters also, you see here also you do not have to install inside, like orifice meter, turbine flow meters, other type of flow meters, you do not have to install anything inside the pipe, or rotor meters also the blob is there which is inside. So, further advantage over other flow meter is that the instrument is one which clamps on externally to existing pipe rather than the being inserted as an excuse me, as an integral part of the flow line. Unlike other flow meters, the ultrasonic flow meter can be installed without any pipe cutting or breaking. Okay, you see that previous slide. To existing pipe rather than the being inserted as an integral part of the. It is a clamp on. You have seen the Doppler shift flow meter is a clamp on systems. We can just outside you install the two sensors. So it will through the wedge. So the ultrasonic signal will enter the pipe. Okay. So, it is totally clamp on system, that means outside of the pipe you install the two ultrasonic sensors, even though there is some problem creates because of the pipe thickness and all this non-uniform pipe thickness, that creates a problem. So, for that reason people started to make the ultrasonic flow meter Doppler shift where the sensors are flushed with the liquids. But if you consider only the clamp on method, so it is more advantageous that it is nothing to be installed inside. So, it is a totally non-invasive technique. There are some advantage of this type of flow meters because of non-invasive method. Unlike other flow meters, ultrasonic flow meters can be installed without pipe cutting or breaking. Therefore, it has enormous cost advantage. The cost is also there. Okay. Its clamp-on mode of operation has significant safety advantages in avoiding the possibility of personnel installing flow meters coming into contact with a hazardous fluid such as toxic, radioactive and flammable ones. If you have that type of liquids flowing through the pipe, so the person who is working on this one, so this is also advantageous. That means if it is clamping on outside, just have a pipe, you just installing on outside like this one to clamp on. So, it has advantage that is person also may be not exposed to this hazardous environment, right, where the fluid might be toxic, might be radioactive, might be flammable, so on. There is some another advantage of this type of meter also in food and drug industry. So, also any contamination of the fluid being measured can be easily avoided. In many situations I have to measure the fluid of the, suppose in the case of beverage industries, soft drinks industries, okay, where the liquid the beverages or soft drinks are flowing in the pipe. So, any installations of the any meters outside, that you have to sterilize the sensors and all those things you have to take, moderations you have to take. But if it is a clamp on outside, especially in that case of ultrasonic flow meter, it does not matter whether it is conductive or non-conductive, I can make the measurement very easily, right. So, in that sense it is also very popular in the food and drug industries. Ultrasonic flow meter have been used mainly for liquids, but are now being applied to gases and streams also. Basically, it was previously used for liquids, but it is used for gases also and streams. Now, there are obviously you cannot say everything is very shiny and very good. So, there are many disadvantages of this type of systems also. What are the disadvantages? Ultrasonic flow meter is sensitive to velocity profile of the flow, right. In the case of electromagnetic flow meter, it is measures the average flow velocity, but the ultrasonic flow meter is not doing actually that, right. That means what will happen, if the velocity profile changes, for the same average velocity I will get different output. This is a problematic case. Excuse me, right. So, alternate flow meters will give different readings for axial symmetric profiles or different shape, but with identical average velocity. If the average velocity is same, but the profiles are not same, so obviously what you will find that you will get different value of the reading, right, the output, which is undesirable. If you assume that the meter coefficient to be 1 for uniform profile, this would drop to 0.75 for a laminar flow, and it will vary between 0.93 and 0.96 for the turbulent flows. So, these are the two typical disadvantage of the ultrasonic flow meter, which is not there in the case of electromagnetic flow meter, but for the non-conducting fluids we have to use ultrasonic flow meter because of its typical non-invasive type of techniques of measurements, right. So, with this I think today I come to the end of the lesson 15 of industrial instrumentation. Welcome to the class of industrial instrumentation. So, this is lesson 16. In this lesson, we will consider flow meter because we are continuing for last several lessons flow meters. This lesson also will cover basically the flow meter, and the contents of this lessons: hot wire anemometer, one of the most widely used industrial flow meters both for the liquids and gases, that we will discuss in this particular lesson. Also we will solve several problems on the flow meter. Various types of flow meters will solve problems, we will give the problems, and also we will provide the solutions to these problems. Obviously, at the end of the lesson, the viewer will know the working principle of hot wire anemometer, both constant temperature and a constant current type. These are basic two types of hot wire anemometer you will find. So, we will cover both, how it works, what is the signal conditioning circuitry, and advantage, disadvantage, everything will be covered in this particular lesson, along with the problems and solution to the different flow meters. Now, hot wire anemometer, if I look at the principal operations, it is based on the principle of heat transfer by convection between the resistance wire and the flowing fluid. The wire is kept at a temperature which is much higher than the surrounding temperature, and hence the name hot wire is given. It is capable of measuring average velocity and turbulent flow of the fluid. It can measure both average velocity as well as turbulent flow of the measurement. This is a great advantage of this particular flow meter. So, there can be two types of schematic arrangement of hot wire anemometers, that is I am telling, either it will be a constant current or constant temperature, right. So, constant current type and constant temperature type or constant RW type. A schematic diagram of the constant current type, you see here actually what we are doing, that initially we are taking all the resistance equal R1, R2, R3 and RW, and this RS is quite high, right, and we can measure, we can see the current which is passing through this hot wire. Now, this resistance is so high compared to this resistance, you will find due to the change of flow, the resistance, even the resistance will change, the change of current will be insignificant, right. So, current is kept fixed at a certain value that can be measured by that resistance, that by the ammeter. What is that ammeter? These ammeters, okay. With the ammeter we can see whether the currents are remaining constant or not. The resistance R1, R2, R3 are of the same order as Rw. Typically, it should be quite small compared to the RS, and the value of RS is high, right. Generally used to, this constant current type is generally used to measure the steady flow of low fluctuations in the velocity, not good for very high frequency terminal flow. We need some compensation. If you do the compensation, then it is possible to that. When lead lag network using, I can make the circuit in such a way so that I can measure the much higher frequency. Otherwise, normally it is not suitable for the low, high frequency fluctuations, so high frequency turbulent of the flow. Now, this is a schematic diagram of a constant temperature type of a hot wire anemometer. You see here it is a auto balancing system. Since RW is put on a one arm of a bridge, which is our hot wire, and all other resistance are put all the same. Now, you see what will happen, that if there is unbalance, that means suppose due to resistance change, then what will happen, you see that if there is unbalance, so you will get a, initially it is balanced, there is no output voltage, no error voltage, okay, but some steady state current will flow through this resistance. Now, what will happen, you see that if there is a change, so that change will be, if there is an unbalanced voltage here, and that will amplify this voltage amplifier, then power amplifier. So, it will give a current. So, it will change the current through this bridge, and it will continue till we achieve the balance, right. So, it is auto balancing systems we can see here. Here it keeps the resistance Rw constant by incorporating the feedback. Now, as the velocity increases, Rw decreases, thereby creating an unbalanced voltage, and the current increases, which brings back the resistance to the initial value, right. It increases the bandwidth and thereby suitable for turbulent flow measurement also. So, it is also for increasing, since we are using feedback. So, it is suitable for measurements of the high frequency swirls and turbulent flow. Now, this is a block diagram of a constant temperature type of sense. As we can see, we have Kb, Ka, E naught is going out. So, this is our typical systems. Thus, we get, you see, delta E naught by V, this is output voltage divided by the change of output voltage due to the change of velocity, Kv, Kb, Ka, Ro, TVS plus 1 plus Kb, Ka, Ki, so which is equal to K dash equal to upon tau dash V S plus 1. Previously, it is only tau V S plus 1. So, what is tau dash V? Let us look at. So, K dash equal to Kb, Ka, Ro, 1 upon 1 plus Kb, Ki, and tau dash V is equal to, now previously we had tau V this, and naturally what will happen if I decrease the time constants of the system, or my frequency response will increase, is not it? Lower the time constants, I can measure the high frequency. This is a very fundamental, fundamental equations of any instruments or any systems. If a thermometer time constant is large, I can measure the response very fast for a step input. If it is cyclic, obviously also that advantage is there. Thus, we see that the system becomes faster since we are dividing this tau V by this factor. So, obviously what will happen by this factor, what will happen is frequency, its tau dash V will decrease, and I can measure the high frequency. Now, comparison of the constant current and constant temperature type measurements. Disadvantage of the constant current types. The current has to be kept large, and with a sudden drop in fluid velocity, it may lead to the burnout of the wire. So, this is a typical problem of the constant current type. That means that current has to be kept large, otherwise what will happen? So, usually it is large, and if there is sudden fall in the fluid velocity, so temperature may rise, because it is constant temperature, some constant current must flow through this one, so it will burn out the wire. For dynamic measurements, separate compensation networks are required. That means I need a lead lag networks, as I told you earlier, to make the phase compensation, so that I can go for the higher frequency of measurement. Constant temperature type removes the above problem with the introductions to the feedback loop. However, there are other problems, instability and the drift problems of there, because drift of the amplifier will come in picture, right. With this, I come to the end of the lesson 16 of industrial instrumentation.